Okay, so yeah, we were gonna have you guys talk about your projects before we do anything. So I was thinking that we'll just go in like alphabetical order by last name. So maybe I have the roster here and I can just like call on you one by one. Yeah, but okay, so I have one thing to announce that's not going to apply to everybody, but for those of you that are in this class and also in Calc 2, I know that I said that the exams would be on the same day, but I was thinking because I already have to have a makeup exam for Calc 2, if you want to take it on Wednesday instead of Monday so that you don't have to take two like math exams back to back, I'm fine with that. So if you want to do that, just send me an email and I'll sign you up for the makeup exam. But that's just for those of you in Calc 2. Okay, so are we ready to go? Everybody ready? Pretty much. Is the makeup? Yes, it would also be at 10 a.m. Yeah. Okay.
So when is the final exam for linear algebra?
It'll be on Monday starting at 12:30, so when our normal class time is, and it'll go to 2:30, so it'll be 2 hours. Okay, cool. Let's see, so who would be first? And if you don't mind, could you turn on your camera at least for like when you are talking, and then you can turn it back off again if you'd prefer to, but you don't have to either. Let's see, I believe the first person will be Amy.
Hi. So mine is on Markov chains.
Mm-hmm.
And I got an extension, so I haven't finished it yet. So yeah.
Okay. So could you say maybe just quickly what's a Markov chain, or maybe like what's an example?
Yeah, so like the Markov chains I'm specifically looking at are like population.
Mm-hmm.
So the whole thing is that like you can tell like let's say 5% of the population moves to the suburbs and 3% of the population moves to the cities. So there would be a matrix that would show like 0.5, no, 0.05 and 0.03. And then you can use that data to tell, and then it'll tell you, hold on, I'm mixing this up in my head. And then it'll tell you like the previous population, and then for the year previous, and then the current population. And then you can use that data to like estimate what the next one is. So basically, you don't need the data from like many years before, you just need the data from the year before.
Mm-hmm. Right. So you get a matrix that describes transitions from year to year, right? Yeah. So yeah, I'm excited to see your project. I do want to mention, since we're talking about Markov chains, that I am going to be offering a class on Markov chains next spring. So if you're at all interested in those, if you take a look at Amy's project and you think it's interesting, then keep that in mind. I would suggest that if you are like definitely interested in that class and you haven't taken probability, it would be a good idea to take that beforehand. It's not strictly necessary, so it's not going to be a prerequisite, but it is really helpful. Yeah. Anyway, so I was going to use that opportunity to advertise. Okay, let's see who's next. I believe is Devin. Yeah.
I don't have a camera, but
That's fine.
my project was on linear algebra in machine learning, because I took a machine learning course last semester and we wrote algorithms, and there was a lot of linear algebra, but I didn't really know what I was doing because I hadn't taken the class yet.
Yeah.
But it's nice to kind of feel more comfortable with it. Basically worked with matrices of data and doing matrix math to apply various algorithms to the data to learn from it. With linear algebra, you use transformations to model a line to fit the data to make predictions from data you know to make new predictions about data.
Okay, yeah, cool. Let's see. Who would be next? Okay, so skip that. I think it's Tony.
Hey guys, can you hear me?
Yeah.
So I did my project on the divergence gradient and curl because we did that a lot it's used a lot in physics. So basically I talked about the del operator and how it's worked and then how it goes with how it's essential to know that for partial derivatives, because it's basically I went through and I broke down the divergence gradient and curl and where and when they are used in physics as well. So I think I did post the video in the group thing. But basically I walked through a couple problems on how to do it, and I color coordinated everything so you can see where certain values are placed in the certain matrix and where you're taking the partial derivatives. Of course, I don't want to like explain everything right away, but I tried to make it so that it makes sense, and then I included a kind of a real life example of where you use it when looking at the direction of steepest ascent. So it was kind of fun and cool because I got to make connections with physics and with linear algebra.
Yeah, good, nice. Okay, so I think we'll go with Corey next. Hi.
Hey everyone, can you hear me?
Mm-hmm.
Okay, cool. So I did my project on coordinate transformations in astronomy. I am your astronomy club co-president, by the way. So basically, I just talked about the two most well-known coordinate systems that are used in observational astronomy, which would be altitude azimuth, which is based on the observer's exact location and time, and then equatorial coordinates, which are more, you could say, universal. But as far as the linear algebra piece, you basically just need a rotation matrix to transform between those two coordinate systems. Where it gets complicated is figuring out the angle that you need to rotate the coordinate system about. It gets pretty complicated because there's like a lot of time dependent parameters and things like that. So the matrix part is straightforward. The spherical trigonometry part is less fun.
Right, yeah. And I saw some diagrams, like some nice diagrams in your project as well, so yeah.
They're really essential for picturing what the coordinate systems are. I think they're kind of hard to conceptualize without the diagrams. So
yeah, definitely. I love having nice diagrams. Something to look at.
They're all from the astrophysics textbook. So
yes, yeah, no, that's totally fine. Okay, let's see. Who would be next? Gareth?
So I thought I'd do a project that's a little bit more out of the ordinary with going to card games such as Hearthstone and Magic and trying to figure out basically kind of a mechanic, but more of a concept that people who play the games talk about called the curve, trying to figure out like using matrices and to properly give, using matrices to find the proper proportion of cards in the deck. So that correspond to costs. In Magic and Hearthstone, cards cost different amounts of resources. and usually there's going to be another resource per turn, and the curve refers to being able to play cards, play a card equal to or multiple cards that equal to that whose costs are equal to those two, and using matrices, solving them out to the deck size would be able to find an optimal amount of these costs of cards to make better decks. Used several matrices for different types of play. So, well, still use matrices, but use different specialized matrices. And I use data from, I focus more on Hearthstone, used decks from that database to basically fill in the matrices to find basically the common amount of cards in between those decks. So I use 10 for each playstyle: aggro, tempo / middle, and then control / longer play, to find the perfect proportion for each type.
Okay, yeah, cool. Okay, so I believe we skipped over Nisa because she wasn't here, but would you mind talking about your project now?
Oh, yeah, definitely. I have done my project on music theory and representation of linear algebra in like music theory and melody matrices. And so it's like there are not much things that like about music theory that is like absolute true that we can say about any kind of like mathematics, but we can say that actually we can represent music and notes in matrices. And like I couldn't get into that much because this is like a huge field that you can just keep experimenting. I just kept in the range of melody matrices, but you can actually do it according to whatever you need to calculate with the music and the tempo and the notes and everything. You can just use matrices in like different size of matrices. You can use like in a different way, however you want. And and in one of them, I actually found a thesis work that I use as a reference that actually I don't know how to say it, like studied the Mozart's Turkish March and about like with the matrices, and I wrote about it, and it was really interesting because you can see like in melody matrices, note vectors, duration vectors, like kind of like rhythmic aspect, and like power vectors, and when you get them together, you can have a melody matrix, and this is used in algorithms. Like you get these melody matrices together, and then you can compare them, and then you can make kind of like perfect algorithm for music. I mean, it's really not something we can say, oh, there's this perfect music, but we can say that there's this music that was accepted by the people, and you can just like get them together and compare it to each other. I think that's pretty cool. And there was this another field that I really wanted to get into, but it was like very limited time, that I found really interesting, that you can actually use linear algebra in frequencies for the music and calculate it. I also wanted to like talk about it too, but then it was just a lot of like different applications, and I just wanted to focus on one of them. It was pretty interesting, and you really don't expect in music, it sounds like super like arty, like it doesn't sound like that's something that you can just use mathematics no matter what, but we can actually represent music with a matrix, like matrix.
Yeah, that's really cool. And yes, there is like a whole field, like a gigantic field called harmonic analysis that is based on this idea of like breaking things down into frequencies. And of course, it gets very theoretical, so it's a pretty detached eventually
Yeah.
from the music, but it is really cool. Yeah.
Yeah, it's so cool. I think so too. Thank you.
Yeah, no problem. Thank you. Okay, so I believe it's Veronica next.
So I'm a statistics AOC. So I did my project on the application of linear algebra to linear regression, which is one of like the core and most essential statistical techniques where you model the relationship between two variables as a linear relationship. You say that, okay, like say student GPA, if we were at a college that had GPAs, and test scores have a linear relationship, I want to model that. If you remember like in high school stats or whatever, it's represented as y equals mx plus b, or like the basic equation for a line in like high school algebra. And it gets a lot more complex. Y equals mx plus b is kind of lines. They don't tell you that. But there's this more complicated way to represent it using your intercept term beta 0 and all of your coefficients. And say you want to find estimates of these coefficients in order to fit your model, and you go through the least squares process. And just the least squares process is just the name for the technique that we use to find the estimates of our coefficients so that we can fit our model. It's actually the next section in the textbook after we had the one we had to read for this class. So you can actually form your model, your linear regression model, that is, as a series of vectors and matrices. So for y equals beta 0 plus beta 1 x plus epsilon, y can be a vector of your response terms. Then you have the design matrix x with all your values for x, and then your parameter vector with all your betas, and then your epsilon vector with all of your errors. And you can represent that as a series of matrices. And then using the values that you have for your x and your y, you can actually solve it out using linear algebra to get estimates, to get your estimates for your coefficients, which is really cool. Linear algebra, all the stuff we've been doing this whole semester. So I think it's cool. Yeah, that's what I worked on.
Okay, cool. Okay, let's see. Is Melanie here? Yeah. Melanie, could you tell us about your project?
Okay. Yeah. I'm a statistics minor, and I did my project on data compression using PCA, which is based on singular value decomposition. So singular value decomposition basically extends the theory of eigenvector or eigendecomposition, but for n by n matrices. And basically you decompose the matrix by calculating the eigenvectors of a dot t a and a dot t and manipulate the matrices to find the eigenvalues. And then once you're and then you can find the maximum direction of each column, and then based on that you can divide it by the sum and get the amount of information stored along each dimension. And through finding each dimension, and you can figure out how much information is stored among each dimension, and depending on what you need, you can take you can determine how many dimensions you need to get a certain amount of information.
Okay, cool. Right, yeah. So singular value decomposition is something that we didn't get to. But it is very, very useful, and it is used in things like image compression and things like that. And so it is something that, it would be nice if we could cover in this class, but usually we don't get to it because it's somewhat far along. But it is good to know because it has a lot of applications, like really useful. Yeah, so take a look at that. Let's see. Who would be next? I believe is Isaac.
Can you hear me?
Yeah.
Yes. All right. So my project is linear algebra and cryptography. So one of the things that I researched and like wrote about was how you can use different methods in linear algebra, such as like row operations or inverse matrices to encode like messages or like ciphers to like kind of like write or like encrypt information. I also went into some like uses of it, such as like encoding. I know that if encoding, you're able to like, or you can use some stuff such as like matrices and some other linear transformations to kind of make like an encryption key. So when you code it, when you like, if you were to like code it out, you could make it so that it's like an automatic process. And to like decrypt it, all you would need is to, for like the simple one that I did, you can arrange like a hidden message in an n by m matrix, and using an n by n matrix as your encryption matrix, you use matrix multiplication to rewrite to kind of like rewrite or to get another matrix that is an encoded version of the original data. And all you would need to do to get like the original data would be to find like the inverse of the encryption matrix and multiply it again to get the original data. And then that's the easiest example that I covered. But yeah, that's what I wanted to do.
That's pretty cool. Yeah, cryptography is one of those interesting like mathematical applications that like is so useful, and it's like really around us all over the place. So it can be interesting to look into those things, definitely. Okay, so we should move on. Next is Kaylee.
Okay, so my project was on the Leontief input-output model, which is an economic model. To spare all the like in-depth details which are in the report, it's basically this guy named Leontief made a model that talks about how every sector of the economy is dependent on each other. He divided his model has like over 500 sectors for an economy, and we can use it to look at input and output. So we can look at how much a certain industry needs to produce in order to get one unit of output in a different industry. We can use it to talk about the prices and things that are going to change. And there's something called final demand, which is the demand that companies have to make their products, as well as demand from the government and demand from consumers. And we can use the inverse of the matrix of the model to determine how final demand affects production. So if final demand increases, how does that affect our production? And if it decreases, how does that influence production? Stuff like that.
Very cool. Yeah. Okay, Megan.
Okay, so I also wanted to do my project on something I've been doing in my physics class this semester. So I talked about circuits and how we can apply linear algebra and systems of equations, and we can derive the system of equations from different laws in physics, and then use that to build matrices and do row operations to understand the current going through complex circuits, because there can be different levels of current in different parts of the same circuit. And to like understand the different values, we can use linear algebra to solve for it easily.
Right. Yeah. Especially when they're really complex, then you don't want to do it by hand. Yeah.
No.
Yeah, for sure. Okay, great. Next is Bo.
Great, can you hear me?
Mhm.
Okay, cool. So my project was on projective space over finite fields. So there's two things there, right? Projective space and finite fields. So in our class, we restricted our attention to like real numbers, to mostly Rn. But you can also define abstract vector spaces to pull from different fields. So the complex numbers would be an example of a different field. But like R is kind of a weird field. For one, it's infinite, and well,
That makes
yeah.
it weird.
Yeah. And you know, it's not infinite like the integers. Integers you can count, but R you can't count. It's uncountably infinite. So it's also weirdly named, because it's apparently named in contrast to the imaginary numbers, but the real numbers are just as imaginary as the complex numbers, and that's important to projection as well, in the sense that, so like, you know, we create the imaginary numbers to fill the role of the fact that we want like the square root of a negative number to exist, right? So in the same way, we want the square root of 2 to exist, so we created the irrational numbers, and that's how you kind of get the reals and so on. And that kind of like forcing numbers to exist. I mean, if you write out the square root of 2, right, it's like a ridiculously long number that's just like impossible to work with. So you know, you might be able to call into question whether it even actually exists. So I mean, it's kind of the same thing, and the idea is just that you know, the reals are very useful space, but we can gain information by looking at other fields. So the other concept is projection, right? So we can think about projection geometrically. You can think about just like, you know, the projection of like a globe onto a wall. If you're shining a light onto a globe, and then there's the projection of the globe onto the wall by a shadow, right? So like we can think about projection intuitively as like an abstraction of shadow. But that's sort of an initial intuition that we had. But it gets more complicated than that, and over time we started to gain more refined ideas of like what projective geometry is. And during the Renaissance especially, right, like we were very interested in perspective and like figuring out how to draw things in the way that we see them. And that's kind of where perspective comes in. And that's how it relates back to the idea of like imagining or forcing certain things to exist. Like a concept central to one of the first intuitions of projective geometry was the point at infinity. So if you have like any pair of parallel lines or any set of parallel lines in a plane, right? You know, in our linear algebra class, we've been saying that if vectors are parallel, then they're never going to intersect, right? But in the projective field, those lines do intersect. They intersect exactly once at the point at infinity, right? And so you can imagine that, you know, take all the parallel lines in a plane, and then they all eventually converge to this imaginary point at infinity. And if you do that for all the parallel lines, all the set of parallel lines all the way around the field, then you eventually get the circle at infinity, right? If you join all of those points, and then you can generalize to get the n-dimensional sphere at infinity or whatever. But I mean, that's kind of an intuition that we had, and that's kind of a messy intuition. Also, you know, you're wondering like, what is that about? And it turns out there's a nice there's a nice way to bring all of these ideas together, and to like generalize over all those intuitions. And that's it can be done linear algebraically. And so that's sort of what my paper talks about a little bit, tries to formulate projective space in terms of linear algebra, and it also discusses projective space over finite fields rather than just over R. But I didn't get to talk about that too much, but it is interesting stuff. So yeah.
Cool, very cool. Yeah, it's really interesting. And I see you have like a diagram, like what happens when you look at projective space over finite fields. It's like, it has some of the same properties, like you can define it axiomatically. But it's like related to this idea of having like points at infinity, which is kind of strange. So yeah, that's a very cool topic. This was stuff that I did in my geometry class last semester, which unfortunately I'm not going to offer again, but yeah, very cool stuff. Okay, I think we have one more, Suji.
Yeah, so my project was on applying linear algebra to like differential equations. So basically a differential equation has derivatives involved, and usually the linear algebra is used in solving a system of differential equations, like particularly linear differential equations where you have a bunch of functions of time, usually denoted as x1, x2, multiplied by some constant and then added together. And that'll equal like the derivative of one function, and you have a system of those equations, and they can model a lot of different things in biology. For example, they can, there's an example that you can have a model of the amount of toxin when you intake a certain amount of toxin. You can model the amount of toxin that enters your bloodstream and the amount that enters your tissue. That's one example, and there's so many other applications of differential equations. And usually you need some form of linear algebra to be able to solve them and look at the overall dynamics of those models. So yeah.
Right, and there's like this idea of eigenvectors and eigenvalues plays a big role in like differential equations.
Especially, yeah, when it comes to solving them.
Yeah, definitely. So there's a huge interplay between linear algebra and differential equations. Very useful. Yeah. Okay, cool. Those were all really interesting. And thank you guys for giving like a short description of what you did. Okay, so I guess we are going to talk about one more thing in this class before it's over. And that is the Gram-Schmidt decomposition. So I have to get this set up. Okay.
Are we going to have a weekly homework for this week?
Yeah, we will have one more homework. Yeah, but I haven't put it up yet. I might make the due date Sunday instead of Saturday, just to give you guys a little extra time. But yeah.
Are we gonna have another quiz too?
No more quizzes. We're done with that. Just the exam. Yeah.
Thank you.
Yeah. Okay. So, right. Like I said, we are just covering the Gram-Schmidt orthogonal. So the idea here, so this is section 6.4. Like I said, we did skip most of 6.3. When do the quiz corrections due? Just get them in by Wednesday, and I'll still accept them. You can still do quiz corrections on I guess on any of them. Just make sure you email them to me instead of like turning them in like I have on like the instructions say on Canvas, because I just want to make sure I actually get them. Oh, problem session solutions. Yeah. I need to write myself a note about that. Yeah. Okay, I'll make sure that those go up. And the final, yeah, I will post a study guide. So I'm hoping to get it posted today. Yeah. Yeah. So look for it today, maybe like later today, but yeah. Okay. Are there any other questions right now? Okay, if not, you can always put something in a chat if you want. Let's see. So 6.3, or sorry, 6.4. This is Gram-Schmidt decomposition. And the idea here is that you have a basis of some space. Maybe it's a subspace, something like this. You can find an orthogonal basis from that. So Gram-Schmidt is just the process that we use to find an orthogonal basis from any basis. So the idea is, so we have the following procedure. Oops, procedure. Okay, so say we have a basis V1 up to Vk of W. And then we want to form a new basis. It's going to be orthogonal. So we're going to define some new vectors. So start with U1, and we'll just take V1 to be U1, right? So this is the easiest part. You just start with the first vector. U2, we want to have it be some version of V2, but we want it to be orthogonal. And so we just want it to be orthogonal to U1, right? So I'm just going to write it this way, and then we'll have a more involved formula. But the idea is we just subtract off the part of V2 that is in the direction of U1, right? So it's V2 minus the projection of V2 onto U1. Then what we're left with is something that is orthogonal to the first vector, right? So, okay, I'm going to try and draw a picture. We'll see how well it goes. Okay, so for when we're defining U2, the idea is we have, say, V1 and V2 that are not necessarily orthogonal, right? But, or maybe, label these differently. So let this one be V1, this is V2. Remember, V1 is the same as U1, okay? And we want to make our vector orthogonal to V1. So we know that this is going to be the projection right here. This is the projection of V2 onto U1, which is the same as V1. And then if we subtract that from V2, we're left with the orthogonal part, right? So this is our U2. Okay. And then we use the same idea. We go starting with V3. We want to subtract off the part that is orthogonal, or sorry, we want to subtract off the part of V3 that is in the plane formed by U1 and U2. So here we're going to project instead onto the plane that is spanned by U1 and U2, right? So we talked last time about how to project onto planes and higher dimensional spaces as well. So we're going to take off that whole part. So we'll get something that is orthogonal to both V1 and V2. Or sorry, not V1 and V2, U1 and U2. Right. Okay. And then we just keep going in this way. So maybe I'll do one more step. So U4 would be V4 minus the projection of V4 onto the span of U1, U2, and U3. V4. Right. So this gets kind of unwieldy as we keep going. But we can write down a nice formula for this. So because we know how to write down these projections, right? So again, U1 is equal to V1, and then U2 is going to be, like we said, V2 minus this projection, which is going to be V2 dot U2 divided by, U1. So it's the projection of V2 onto U1, U1 dot U1 times U1. Right, that's the formula that we had for the projection. Okay, and then for U3, we start with V3. We subtract off the part of this vector that is in the direction of U1, as well as the part of this vector that is in the direction of U2. So that ends up being this projection onto U1 minus also the projection onto U2. Right? Okay. And then we would just keep going in this manner. So we'll do one more. So for V4, we start with V4 and then we subtract off the projection onto U1 and the projection onto U2. And the projection onto U3. Okay. So the idea here is you're just building up an orthogonal basis, like one vector at a time. So you start with your first vector, then you create your second vector that is orthogonal to the first vector. You create your third vector that's orthogonal to the first two vectors, and so on. You just keep building it up. And then you're guaranteed at the end to have something that is orthogonal and also linearly independent, right? If it's orthogonal, it will be linearly independent. So it should span your space. So we're not going to go over the proof of that. It is in the textbook, but I think we will just do an example of doing this. Okay, so say we have the following. We have, so these will be vectors in R4. So we have V1, V2, and V3. And so W, we'll say, is going to be the span of these. And you can check that these would be linearly independent. So this will be a basis, right? is a basis. Okay, so let's form an orthogonal basis using Gram-Schmidt. Okay, so the first step is we just let U1 equal V1. So that is just that first vector, minus 1, 1, 0, 0, right? And then U2 is going to be V2 minus the projection of V2 onto U1. Okay, so that's just the formula. So let's fill in what this will give us. So maybe give myself some more room. Okay, V2 is minus 1, 0, 1, 0. And then we take V2 dot U1, which is right here. So, okay, I'll write it out. So it'd be minus 1, 0, 1, 0 dot minus 1, 1, 0, 0 over that dotted with itself times this vector. Okay, so if we compute the dot product, maybe I should clean this up a bit. In the numerator, we would get 1, and all of the other terms in the dot product are 0, right? So we get 1 over the denominator gives us 1 plus 1, so 2, right? Okay, so we get, actually, I put this right here. Okay, try to do this. Let's see, that's negative, negative. So negative 1/2 plus 1/2, so minus 1/2. Then we get here just negative 1/2. There is 1 minus 0, so 1, and that's 0 minus 0, so 0. You guys agree? Okay, cool. Right, so that's the first, or no, that's the second vector, and then we just have to do U3. And so just let's write down the formula for this. So V3 dot U1, U1 dot U1. Oh, and that's it, yeah, on U3. Okay, so what is V3? It is minus 1, 0, 0, 1. And this first part, you get minus 1, 0, 0, 1 dot U1, which is right here, it's minus 1, 1, 0, 0. Oops. Okay. Okay. Times that vector minus, let's see if maybe I'll move this over. Okay, for this term we get V3 dotted with U2, so that's this guy right here. So we dot with minus 1/2, minus 1/2, 1, 0 over, okay. times that thing. Okay, so let's work out what this would be. Computing the dot product, we should get 1 there. And in the denominator, 2 again. Yeah. Okay, so that's that first or second term. And then here we get 1/2 plus 0. Okay, so just 1/2 in the numerator. And the denominator gives us 1/2 plus 1, 3/2. Yeah, I think so. Okay, and then it's just a matter of simplifying. So here, I'll just insert this scalar. So we get 1/2 minus 1/2, 0, 0. And this will simplify to 1/3, right? Okay. Times this. Maybe I'll stick it in. Okay. Plus the vector, so that'd be 1/3 times 1/2, 1/6, 1/6, and negative 1/3, 0. Okay, and then it's just a matter of adding these things up. Okay, so 1/2 plus 1/6 is 4/6, which is 2/3, which is minus 1, so negative 1/3. And then this is, I think, 1/3, and that's negative 1/3. And that's 1.
Pardon me.
Yeah.
So in the second row, that would be negative 1/2 plus 1/6. So it'd be negative 1/3.
Yeah, you're right. Okay, there we go. Cool. So that gives us our U3. So we can go ahead and write down our basis. Remember, this will be our orthogonal. And let's just write down our final answer. So the first vector we got was minus 1, 1, 0, 0. The second vector was minus 1/2, minus 1/2, 1, 0. Was that right? 1, 0. Yeah. And the third vector was this one right here, minus 1/3, minus 1/3, minus 1/3, and 1.
Could you scale it by multiplying U2 by 2 and U3 by 3?
Yeah.
Oh, okay, cool. But you don't have to.
You don't have to. If you did want to, you could, yeah, definitely do that. And then if you were actually looking for an orthonormal basis, remember that's just a basis where your vectors are orthogonal and also each have length 1. If you wanted to get that, you would just take each of these vectors and divide by its norm, right? So you could do that if you wanted to. Okay, and so maybe I will, yeah, we'll do one more example. Here, I'll just move it to this next. Okay. And so say we have this subspace This will be a subspace of R3 given by the span of these two vectors, right? And first we will find an orthonormal basis. So I'll break this into parts. For W. And then also we will extend it to an orthonormal basis on R3. Okay, so the first part is straightforward. First we use Gram-Schmidt. So this is a solution. Right, so let's label our vectors because that will be nice. So this will be V1 and that will be V2. And we take U1, so there's only two of them, so this shouldn't be too terribly painful. U1 will be V1, so it'll be 1, 2, 2. And U2 will be V2 minus V2 dot U1 over U1 dot U1 times U1. So V2 is minus 102 minus this dot product. So if we work out what that will be, okay, I'll write it out. 122 dot minus 102 over this guy times that. Oh. Oh, I flipped everything. Okay. Minus 102 should go here. And U1 is 1, 2, 2. 2, 1, 2, 2, 1, 2, 2. There we go. Okay. This is going to give us -1 plus 4, so 3. And this is going to give us 1 plus 4 plus 4, so 9. Yeah. Times 1, 2, 2. So we get, let's see. Maybe I'll write it up here. This will be 1/3 out front. So we will get -1, minus 1/3, 0, minus 2/3, and 2 minus 2/3, right? Okay, so if we go ahead and simplify these, minus 4/3, minus 2/3, and that would just be 4/3. Okay. So we have our two vectors, but they're not necessarily orthonormal, right? So I'm going to define W1. This will form our orthonormal basis. It'll be 1 over the norm of U1 times U1. And W2 will be 1 over the norm of U2 times U2. Right? So the norm is just where we take each of the entries and square it, we add them up, and then we take the square root, right? So it'll be 1 plus 4 plus 4 times 1, 2, 2, which is 1 over the square root of 9. So we get 1/3 times 1, 2, 2, right? Which, if we want to write it as one vector, is 1/3 2/3, 2/3. And then we want to find the norm of U2. So that is going to be where we take each of the entries and square them. And take the square root. And then we multiply by the vector. So if we just work out what this is, we should get 16 plus 4 plus 16 over 9. Right. Times that vector, which I won't copy again, but this would be root 9 over 36. Oh, that should be a 3. Anyways, and then you can work out what this would be. So if you simplify, I guess this would be, maybe let's do this off to the side. So this is root 9 over root 36, which is 3 over 6, which is 1/2. So negative 4, 6, negative 2, 6, 4, 6. Okay, so that was the process of finding the orthonormal basis. Guess let's write down our answer. So we got 1/3, 2/3, 2/3, and that can simplify. So 2/3, 1/3, 2/3. Right. Okay, cool. So that would be our answer for the first part. The second part wants us to extend this to an orthonormal basis on R3. And first we should just extend our, so we had our collection of V1 and V2 that spans a subspace of R3. We can just extend this to a basis of R3 by finding another vector that is just linearly independent with both of these, right? On R3. And so let's see what I'll just copy this. V1 and V2 were 1, 2, 2, and -1, 0, 2. Okay. And sort of the easiest way to find another vector that is linearly independent with these, we just need to find one. We don't need to find a particular one, just anything that will work. We know that V1, V2, and V3 are going to be linearly independent. If and only if the determinant of the matrix formed by just putting these in as the columns is not equal to 0, right? So remember that so this is saying that the columns of this are linearly independent, right, of this matrix. So we just want to find a vector whose determinant, or, okay, let me write this out. So plugging in V1 and V2, we get 1, 2, 2, -1, 0, 2. We just want to find some entries for here that will make the determinant of this matrix not 0, right? And so I think the easiest way to do that is, notice we already have a row with 1 0 in it. If we put another 0 in it, that's going to make this determinant easy to calculate, right? Because we'll just use that row to expand it. Okay. And then we can just choose some values. So I'm just going to write out, so if we start computing the determinant, and so we're leaving these blank for now, we're going to fill them in a second. We would get -2 times the determinant of -1 blank 2 blank, right? And then the other terms of this expansion are 0. So we just need to fill in some numbers that will make this not equal to 0. So if we just take 1 and 1, we should get something non-zero, right? So if we take the determinant of that, that's -1 -2, so -3 for this 2 by 2 determinant, which would give us 6 here, right? Okay, so now I've found a vector that is linearly independent. So V3 will be 1 0 1. And if you did this process, you might have found like a different vector. That's totally fine. We just needed to find 1, right? Okay, so now that we have our basis for R3, so then this will form a basis. We already have 2 orthonormal vectors, and we just want to add one more. So we're just going to do the third step of our Gram-Schmidt decomposition with V3. So we take V3 minus V3 dot U1. U1 will be easier to use than W1, so we'll just use that since it's not going to change anything. Minus V3 dot U2. And that should give us something orthogonal to both U1 and U2. And then we'll just normalize it to get an orthonormal basis. Right? Okay, let's see. I can go through this computation if you guys want, or we don't have to, since it'll be like the same thing as what we've been doing. Does anybody feel very strongly about it? Not really? Okay, well, I'll just leave this to you to finish for practice. Oh, sorry, I shouldn't say this is V3. This is U3. Okay, and that is all we are going to do for linear algebra. So this is the end. Yeah, so I will be posting the study guide and also solutions for the problem sessions. And there will be one more problem session this week, so I'll post that later today. And if you have questions before the final, feel free to email me. Let's see, I'll have office hours today and also on Wednesday, but not on Thursday. But you can still email me if you have questions. And yeah, so good luck.
Can I ask a quick question? So like if we find out this U3, do we then say that U1, U2, and U3 is an orthogonal basis for R3?
Yeah, then it would be an orthogonal basis for R3, yeah.
Cool.
Yeah.
Thank you.
Just a question, for any subspace, is there like several orthogonal bases?
Yeah, so you could just imagine like you have a subspace, you just pick any vector in any direction that sits in your subspace, and then you can start constructing an orthogonal basis, right? So by just finding a vector that's orthogonal to it, and then you add another one. The only time that doesn't work is if you have like a one-dimensional subspace, because then you know, there's nowhere to go from there. But yeah, basically you could imagine just starting in any direction, and then you can construct an orthogonal basis from that. Okay, well, yeah, this was great. Thanks for being such